Hey everyone, this video I'm going to focus on how to actually calculate the correlation coefficient. So I'll take you through kind of the manual calculation. I'm going to be doing a lot of it in Excel here, as you see. And then in a future video, I'll show you how to do this on like a TI-84 or TI-83. All right, so the data set that I've chosen to do the calculation, it's a small data set. It was actually a larger data set, but I just took a subset of it. It's data that came from many different countries around the world, but these ones are mostly developing countries. We recorded two things, the number of internet users per 1,000 people and the average life expectancy for that country measured in years. And so we have the data here in columns A and B. I've already created a scatter plot. And as you can see, there's a pretty, moderate to strong positive linear association between these two variables. Countries that have more internet users tend to have a lot longer life expectancies. So I threw out the word moderate and strong, but we want to quantify that the strength of this relationship. And this formula up here is the correlation coefficient. That's how we quantify it. So we use the lowercase r to represent it. And it's really kind of like an average. So if we look at the different components in the formula, here in this first set of parentheses, what we have is a formula telling us to calculate the z-score of an x value, right? So take an individual x value, subtract the mean of the x values, divide by the standard deviation. In the second set of parentheses, we have the same thing, but for the y values. So this part of the formula is telling us to standardize or find the z-scores of the y values. And the fact that they're in parentheses next to each other, that's telling us that we need to multiply or find the products of those two z-scores. And then the fact that we're summing and then dividing is like averaging, right? So we're averaging the product of a bunch of z-scores. All right, so to convert both of these variables into z-scores, we need to find their means and their standard deviations. Okay, I will not be doing that by hand. I'm just going to have Excel do that. So use command average. Okay. So for the countries in this data set, the average number of internet users per 1,000 people is about 100. So that's like 10% of the country has internet access. Okay. And then let's find the standard deviation. It's about just under 50. And we'll do the same thing for life expectancy. Find the mean. Excel just calls it the average. And then the standard deviation. Okay. All right, so from here, we're going to convert both of these columns of data into z-scores or standardized values. Okay, so let's call this z-scores for x. Right. So I will take, let's see, take the first x value, probably need a parentheses. Take the first x value, subtract the mean, which is 101 point, just call it 31. Rounding there, and divide by the standard deviation. We'll call that 49.62. And then we will apply that to everything else, every other value in the X list, right? Internet users per 1,000 people. And then in the next column, we'll calculate the z-scores or the y values. First y value, subtract the mean, so let's just round it to 72.32. Divide by the standard deviation, we'll just call that 4.43. And then we will apply that same procedure to the rest of the y values. So what I've done now is I've transformed the original values, right, from the raw data into z-scores, right? So I've taken care of this part of the formula. All right. Now, it'll be interesting to see, what this would look like if we graphed the z-scores. So let me go ahead and highlight this, and I'll insert a graph. So it looks an awful lot like the scatter plot of the original data, right? Like if you just focus on the blue points, right, the pattern looks identical. Right? The only difference is the scale, right? The x-axis here has a scale from 0 to 200. Here, the x-axis, well, it's in standardized units, so it goes from -2.5 to 2. The y-axis originally is in years, so that's 60 to 80 years. But when standardized, it's -2.5 to 2. So visually, like if we just look at the pattern made by the dots, it looks exactly the same. It's just the scale has changed. So let's move that here for now. All right, so then the next thing that we need to do for this formula is we need to multiply each pair of z-scores. So I'll write here product of z-scores. And that's just a matter of me saying, all right, let's take that value and multiply it by that value. And we'll repeat that for everything. Okay. So what happens here? Well, if the z-score for x and y are both negative, meaning that the data point falls over here in quadrant number 3, I think, right? Then the product will become positive. Likewise, if the z-score for both x and y are positive, meaning the data point falls over here in quadrant 1, okay, then the product will also be positive. Okay? So when we look at our scatter plot, we see that most of the data, because it's a upward trend, falls in quadrant 1 and in quadrant 3, meaning the z-scores are going to have the same sign. They're either both positive or both negative. And when two quantities have the same sign and you multiply them, then the product will be positive. So most of what we have here are positive numbers. Okay, there are a couple of negatives because we do have some points in quadrant 2 and quadrant 4, but not many. Okay, so that's going to be important in just a minute. All right, next we need to sum all of these products. Okay, so I'll just write the sum command. And then finally, we need to multiply that sum by 1 over the sample size minus 1. Okay, so I will do 1 divided by, now what's the sample size? This is row 14, but the first row is just a label, so it's 13. Okay, so 1 divided by 13 minus 1. And then we will multiply by the sum. I think I did not do my parentheses correctly. Let's try that again. Okay, so I wanted 1 divided by the quantity 13 minus 1 times the sum that I had. And that looks right. Okay. I knew there was something wrong because the correlation coefficient has to be between -1 and +1. So I'm looking for a decimal value. So there it is. Oops. So 0.8. So, my original description was pretty accurate. This is moderately strong. It's more towards the stronger side. It's pretty close to 1. All right. So did I do it all correctly? Well, in Excel, there is a command to just calculate the correlation coefficient. I think it's just CORAL is what they call it. All right, so I need to input the x values, followed by the y values. And there it is, right? So when Excel, does all the computation itself, it gets a correlation coefficient of 0.80, right? It matches ours, okay? There are some differences, like at the 4th decimal place, but that's because I rounded the means and the standard deviations when I was calculating my z-score. So that's the reason for, the minor differences. All right, So why does it make sense that the correlation is positive? What did I do? Because of the positive trend, right? And I was mentioning that, most of the points are in quadrant 1. Okay? So both z-scores will be positive, therefore the product will be positive. And you also have a lot of data in quadrant 3, okay, where both z-scores are negative, yet the product will still be positive, right? So this column here is dominated by positive values, okay, which is how the correlation coefficient comes out to be positive. But think about it, right? What if most of the data was in quadrant 2 and quadrant 4? In quadrant 2, you'd have maybe you'd have a negative z-score for x and a positive z-score for y. So the z-scores would have opposite signs, so the product would come out negative. And if you had a lot of data in quadrant 4, there the z-score for x is positive, but the z-score for y would be negative. And so again, different signs, the product would be negative. And so if you had a downward trend, meaning most of your data are in quadrants 2 and 4, right, then you'd have a lot of negative values dominating, that column of products, and your correlation coefficient would come out to be negative. So just to go back to the original graph here, let's go ahead and add some lines, right? So we know the means for our 2 original variables. Okay. So the mean number of internet users was like 101. And put a line here for that mean. And we know the mean of life expectancy was about 72, 72.3. We can put a line right about there. All right. So when you have a lot of data that are above average in both variables and below average for both variables, right, you're going to end up with a positive correlation. All right. Now, something I didn't mention is, well, what are the units of the correlation coefficient, right? We know the value. So we know the value is 0.80, right? But, is that 0.80 years? Is it 0.80 people, internet users per 1,000? Well, actually, the correlation coefficient has no units. Okay. So correlation coefficient has no units. Not units, no. Okay. And this should make a little bit of sense because it's based off of z-scores, right? And z-scores are kind of themselves unitless, right? These numbers here don't really have any units to them. These are not years. These are not internet users per 1,000. This is just kind of measuring, number of standard deviations from the mean. So just keep that in mind, that the correlation coefficient is simply just a number that represents strength, and it does not have any units to it. All right. Something else that probably now would be a good time to discuss is, the fact that the correlation is pretty high, right? There's a 0.80 correlation coefficient between these 2 variables, right? Which is pretty strong. So should we then infer that, how can we help countries who have low life expectancy? Should we just try to get, provide more internet access to those countries without solve the problem? And the answer is no. That's kind of silly, right? I don't think giving people internet access is going to help them live longer. And so it's kind of a fallacy to think that a high correlation means that one variable causes another. Okay. In this case, these variables are kind of a product of the wealth of the nation, right? Wealthier countries have more internet access, or more developed, but they also have longer lifespans because they have better healthcare, they have better access to medicine, they maybe have access to healthier food. So it's not that the internet is causing people to live longer. It's the fact that there's a third variable which was not even measured in the study, which is the wealth or the affluence of the country itself. So you'll probably hear this many times over and over, but correlation does not mean that we have causation. Okay? Two variables can be very strongly correlated, but neither one causes the other. Okay? They could both be, again, a product of some third variable that you haven't even measured. So thank you so much for watching this video. I'm going to make one more video on correlation where I do it on a TI-84 so you can see how it's done and know the commands there.